Yeah, this is going to get into section 3.5, chapter 3, section 5. We're going to learn about derivatives today. Derivatives are the opposite of integrals. All right. Remember I showed you this thing here? Oh. When I did this, d of x. Remember I showed you this? Let's make an x squared. All right. I showed you this. A derivative actually is doing it the opposite direction. This is how derivatives work. If I'm going to take if I've got f of x equal to x squared. Now before we did the inverse of this and we used the f prime of x, it's also a derivative. It's also showing derivative. Here's how this works, and this is called the power postulate, or power, what do they call it? The power, go to, am I graphing inequalities? I'm on the wrong page. This is 3.6. We're supposed to be in 3.6, so this should be 3.6 here. Yeah, that's just real. Tangent to a curve. And if you take a look on page 151, you're going to see there's different properties here. There's the common rule property, they call the power rule property, they call it different properties here. This is what a derivative is. You take the exponent of what's up here, and your exponent up here, you multiply this by the coefficient that's out in front, and you subtract one from the exponent. So this is actually 2 times x, and it's going to be 2 minus 1. We're going to subtract that down, which would mean it's really 2x when we take derivative of, okay, you multiply the exponent times the coefficient, it's all front, and there's a 1 out there. All right, and then you subtract 1 from the exponent. So we would go, this is 2 times 1, right? And then we subtract 1 from the exponent to give us 2x. This is called taking derivative of it. Let's take a look at another one. If I said f of x equals 3x cubed, and we wanted to find the derivative of, right, it's going to be 3 times 3, yeah, and then 3 minus 1 up here. So we would have 3 times 3 is 9x squared would be the derivative of 3x cubed. These are called derivatives. You will be using these a lot coming up. Derivatives, we're going to do first derivatives, we're going to do second derivatives. In physics, a first derivative is acceleration. Second derivative is velocity, I believe, if I remember correctly. Okay, so you'll starting to use this when you see in physics. We'll actually use this a little bit in here too. Okay. All right, that's called a first derivative of a problem. So if you were going to, let's say, have more of an f of x function, let's say 3x to the fourth plus 2x third plus 5x squared plus 6x plus 9. Looks like a lot, huh? It's really not. F prime. What's the first one going to be? So it'd be just 12x cubed, right? What would the second one be? 6x squared. What's the third one? 10x. What's the fourth one? Just 6. 1 times 6. This goes to 0, right? There's a 1 there. We subtract 1. X to the 0 is just 1. What's this one then? Just nothing. It goes away. Because we really have x to the 0 there. Right? That goes away. Gone. So this would be your first derivative right here of that top one. 9 goes away. Okay? What if we had an f of x that looked like this? Same way, but now you have to remember you have negative exponents, so you subtract, they get bigger. So your f prime of x is going to equal negative 9x to the negative fourth plus negative 8x to the negative 3 plus x to the negative 2, and that's as far as we go. 1 goes away. Okay, we're subtracting each of these exponents by 1. Looks goofy, doesn't it? Now we're going to be able to tell. Remember I told you this first derivative tells you stuff? Like acceleration and velocity and taking derivatives. This also tells you, let's say we have a graph like this, and we pick a point right there. It'll tell us where the tangent line is on that graph. It only hits the graph at one point. All right? Only hits that graph at one point right there. All right? That's called a tangent line. So let's take an equation. Let's say f of x, we'll make an easy one here, is x squared. F prime of x equals 2x. And we graph this out, we get a parabola like this, something about. That's an ugly parabola. Okay? We get a parabola like this. And I want to know what's the slope? Really what we're given here is the slope of my tangent line at a certain point. So I want to take a look at x at, let's say, 5. Okay? When x equals 5, I put that into my f prime, or my derivative of x squared, and I find that it's 2 times 5, which equals 10. So if I went up here, 1, 2, 3, 4, 5, and I went out here and I found my point, that would be the slope of my line at that point. That is my line. At that point of 5, I would have a slope of 10, or 10 over 1, if you wanted to graph it. You'd find the point and you go up 10 and over 1, and that would be your slope of your line. Okay? The key point is in here is knowing how to do a derivative, all right, and then knowing what that derivative gives you on your graph. Notice I graphed the x squared. All right? I graphed the original function. I took the derivative of it, and I plugged in a point into the derivative to figure out what my slope was at that point. If I had to put 2 in here, all right, let's say 2 is right here, f prime of 2 equals 4, up 4 over 1, I'd be looking more like this with the slope of my, at that point, with this tangent line, or the slope of that tangent line at that point. All right? Pretty easy? Good. They have different rules. If you take a look on page 151, you can look at the different rules up on top. Probably the only one I didn't cover in this would be the sum rule, that if you add two functions, let's say g of x and h of x that equals f of x, then g prime of x, or the derivative of it, plus h prime of x would equal f prime of x. Probably the only one I didn't cover. I don't think we'll be doing much with that one, but you can take a look at that. So what I want you guys to do on page 153, let's do the even ones. Let's do, let's see, even 16 through, let's see, find the equation, tangent line, 16 through 32. Even. 16 through 32. The last two problems, they're asking you to graph. I do want you to graph those. All right? So graph those last two problems, 30 and 32. Page 153. Page 153, 16 through 32, even.